Section 2.6. For these examples, you're going to want to first review the PowerPoint presentation on Section 2.6 over quadratic functions. The first example in the PowerPoint deals with finding the vertex, x-intercepts, and the y-intercept of a given quadratic function. So the first thing we're going to do is figure out the vertex. Well, the vertex is determined by x being equal to negative b over 2a. In this case, our b is the negative 5, so it's the opposite of negative 5, all over 2 times our a value, which is 3. So our x value is 5 over 6, 5/6. This is our x-coordinate in our vertex point. So I now know my, again, x-coordinate is 5 over 6. All I have to do now is come up with my corresponding y value. And to do that, you just plug in the x, 5 over 6, into every x in the given function to figure out the corresponding y value. So you would get what here? Well, you can just use your calculator if you wish. Probably be a good route to take. And if you work all this out, I believe you get negative 49 over 12. Again, you can plug that in your calculator. That's just fine. Corresponding y value is 49/12. So the vertex of this particular quadratic function, which graphically is a parabola, is 5/6, negative 49/12. The next thing we have to do is determine the y-intercept, or excuse me, the x-intercepts. You could determine the y-intercept. That'll take 2 seconds, but we'll do that in a minute. Anyway, the x-intercepts are always determined. When you're looking at something graphically, the x-intercepts are always determined by letting the y, or f of x, be equal to 0. And so now you're going to have an expression purely in terms of x. So this is a quadratic equation. We looked at these types before. If it's possible to factor, then go ahead and do so. Let's see, is this one factorable? Let's see, I believe it is. Let's see, does that work? Yeah, negative 6 plus 1, negative 2. Okay, so if possible, go ahead and factor quadratic equation and then solve for x. Or if that does not work, you can always use the quadratic formula. Okay, so here we get what? We set each binomial equal to 0. Setting 3x plus 1 equal to 0 would give us x equals negative 1/3. Setting x minus 2 equal to 0 gives us x equals 2. So our x-intercept points would be what? Our x-intercepts would be what? Negative 1/3 comma 0. And also this point to 0. These two ordered pairs, these 2 points on the x-axis would be our 2 x-intercepts. The y-intercept, like I alluded to a little bit ago, piece of cake. The y-intercept is always determined when x is equal to 0. So you let every x be equal to 0. Well, guess what? If every x is equal to 0, you just get the constant term. Okay, so the y-intercept, if it's being looked at this general form of your quadratic function, is always just going to be the constant term or the c term, so negative 2. This, in terms of an ordered pair, would be 0, negative 2. There's your y-intercept. Okay, the next thing we're going to be looking at here is solving a system of equations in which at least one of them is now quadratic. Okay, so we're looking at slide number 5 in the PowerPoint presentation, slide number 5, example A. Well, in this particular case, probably the best thing to do would be to recognize that y equals y. Both of these function notations are indicating y's. Okay, so we know that y is equal to y. So let's go ahead and just make this expression in terms of x be equal to this expression in terms of x. And now we have an entire equation purely in terms of x's, which we could solve, okay? So I don't like fractions personally, so I'm going to eliminate them. And that goes back to the least common denominator, which is 2. So I'm going to multiply both sides of this equation by 2, and that will eliminate my fraction. So here we get what? 2 times 1/2 x is just x, plus what? 2 over 2 reduces to 1. 1 times 3 is 3. On the right side, you get 2x squared minus 10x plus 12. And notice now my fractions have been eliminated. At this point, I'm going to set this thing equal to 0. by subtracting x from both sides and also subtracting 3 from both sides. So 12 minus 3 is there's plus 9. Again, just like in the previous example, once you get to this point, you're trying to solve for x, and you could do that by either factoring or by using the quadratic formula. Let's see, I believe this one is factorable. Let's see. Let's see. I believe that works. -9, -2, -11. Yep. And the first and last also work. So again, you said each binomial equal to 0 and solve for x. That's going to give us a 9/2 and a 1. Now you're not finished here. What you actually just determined are the two what? Are the two x coordinates of your 2 points of intersection that exist. All right, you have a line here and a parabola. So graphically, it's going to look something like this. There's your parabola. There's your line. You're going to have perhaps 2 points of intersection here. And that's exactly what we have in this particular situation. So how do we determine the corresponding y values? You plug them in. So you can use either one. Doesn't make any difference. Let's see. So if x is equal to 9/2, why don't we just do this? F of 9/2. All right, so you get 1/2 times 9/2 plus 3/2. Here again, just use your calculator, and you should get 15/4. And then if x is 1, replace every x with a 1 here. So f of 1 would be what? 1/2 times 1 plus 3/2, which would give us 1/2 plus 3/2, 4/2, or 2. Okay, so therefore we have 2 points of intersection. Okay, 2 points of intersection. Where? At, let's see, 9/2, 15/4, and also at 1, 2. Okay? Solve a system of equations in which at least one of them is quadratic. That's what we're doing now. Let's do another one. Okay, so the second system of equations we're going to be looking at here involves 2 quadratic functions. I'm going to go ahead and handle this the same way I did in the previous example, letter A. Again, we're looking at examples that are in the 2.6 PowerPoint presentation. Okay, so we know y is equal to y. That's reflexive property of equality. So let's go ahead and just let this function in terms of x be equal to this function in terms of x. And now we can solve for x. So I'm going to go ahead and add an x squared to both sides. I'm going to add an x squared to both sides. Give me a 2x squared on the right. I'm going to subtract 2x from both sides. Give me a -2 on the right. And then I'm going to subtract 6 from both sides. Give me a -12 on the right. So 0 now equals this. Okay, well notice the GCF here is 2. Why not pull out a 2? That's going to make our factoring process a bit easier. Okay, now we have this. If you divide both sides by 2 now, well, let's just go ahead and show that. You get what? Guess what? 0 equals x squared minus x minus 6. Okay, so at this point, remember, you can either factor it if it's possible to do so, or you may use the quadratic formula to solve for x. In this case, it is again factorable into the product of these 2 binomials. So again, you let each binomial be equal to x, and we get what? A +3. Here, you let each binomial be equal to 0, and you solve for x. Okay, you let x minus 3 equal 0, solve for x, you get 3. You let x plus 2 equal 0, solve for x, you get -2. Again, these are the x coordinates in your 2 points of intersection. Okay, so this graphically looks something like this. You got 2 parabolas, one opening up, one opening down, where you could have 2 points of intersection occurring. And that's exactly what's going on in this particular situation. Okay, so what are the 2 points? Well, okay, let's figure them out. If x is 3, let's just use g of x, all right? So if x is 3, what's g of 3? And you could use either function to plug in your x coordinates, and they'll spit out the same y values, okay? So g of 3 would be what? 3 squared minus 6. So g of 3 would be what? 3. And then if x is negative 2, what's g of negative 2? G of negative 2 is the same as negative 2 quantity squared minus 6. So that's 4 minus 6, or negative 2. So therefore, 2 points of intersection where? At negative 2, and also at 3, 3. Okay? Again, we're looking at solving a system of quadratic equations.